Go. Hello everyone. Today in this video we are going to talk about the electromotive force of a cell and internal resistance of a cell. So let's start the video. So electromotive force is the electrical pressure given by a source like cell for the flow of charge. So it is defined as the work done by the source to move a unit positive charge from one point to the same point going through all the circuit in one round. So whatever energy is given by the cell for a charge to flow through the circuit for one round is electromotive force, and its definition is work done by a source taking a unit positive charge around the complete circuit. And another definition is also there. So it is a potential difference between the terminal of the cell when this circuit is switched off. So electromotive force is a potential difference across the terminals of the cell when the current is not flowing through the circuit. So we'll talk about it later. So sources of EMF are cells and generator. So and unit of EMF is volt. It is same as potential difference, but it is not the potential difference. Potential difference happens between 2 points of a circuit, but out here the EMF is between the terminals of the cells when no current is flowing, but potential difference may occur anywhere within the circuit between 2 points. Okay, these are the difference. So as I have said, potential difference, EMF is the potential difference between two terminal when the circuit is open, and out here it is the difference in the potential between any 2 points in the circuit. So it happens when there is open circuit, no current flowing. Out here it has to be closed circuit, current should flow. So EMF is a cause of potential difference. So we call EMF is cause and potential difference is effect. And EMF is always larger than potential difference, and potential difference is less than EMF, and it does not depend on the resistance of the circuit. So as we all know, EMF is the potential difference when there is nothing connected to the circuit, like it is open circuit. So but it out here potential difference, it depends on the resistance of a circuit, because V is equal to IR. If the value of resistance is more, so potential difference will be more, but out here it is independent of the resistance of the circuit. So next, internal resistance. So when the current flow through a circuit, it has to go through the cell also, and inside the cell there is some resistance due to the presence of electrolyte electrodes. So this internal stuff will also give some resistance to the current, and that's why we call it internal resistance of a cell. So it depends on the several factors. You can read its nature of electrolyte, that means what kind of chemicals you are taking inside the cell, electrolyte, and it depends on the concentration. So if the charge carrier are more, so resistance will be less. So it depends directly on the distance between the two rods. If the rods are kept far away, so charge has to flow through the electrolyte for the long time, so it may offer more resistance. So it varies inversely as the common area. Common area means suppose you have two electrode like in the form of plate, and if you are dipping one plate fully and one plate partially, that is half of the plate is inside, so that means the common area for both will be only the half plate, so half the area of the plate. So it depends. So if you have more area, more charges can enter the electrolyte. So that's how it is inversely proportional. More the area, so less the resistance. If the area is more charge can enter and come out of the cell at a time. So it depends on the temperature also. It increases with decrease in temperatures, inversely proportional to the temperature. Not inversely proportional, but it decreases with increase in temperature. So this is all about the internal resistance. Now let's derive the relationship between EMF, terminal potential, and the internal resistance of the cell. So we are considering a circuit. Now as you can see, this whole part is cell. Now not only these two lines, but this whole part is cell, and inside there is some resistance also, internal resistance, which is denoted by small r, and EMF is the EMF of the cell. So now these are the all assumption. EMF is E, internal resistance R, the capital R is the external resistance. The cell is connected across this external resistance capital R. I is the current flowing, and V is the potential difference between this cell, and small v dash is the potential difference across this internal resistance. So from the definition we know EMF is work done to take the unit positive charge across the circuit. So we can say it is a work done from A to B and B to A again. So A to B is external circuit and B to A is internal circuit. So I can write this WEB. So as we all know, potential is work done by charge. So work done is potential into charge. So I can write, instead of WAB and WBA, I can write V Q and V dash Q, as all we have already assumed that potential across R is V and potential across small r is V dash. So next is, now this is the last equation. So as from the definition, like EMF is work done is taking the unit positive charge, that is Q is 1 coulomb. So I can write, so if you put Q is equal to 1, then you will get E is equal to V plus V dash. So now again I can use Ohm's law in this V. So V is equal to current times resistance. So V is for external resistance R, so that's why I'm writing IR, and V dash is for internal resistance, so I'll write I small r. So now after putting values, so I'm taking I common, so your I will be EMF plus sum of resistance of the circuit, so that is internal resistance plus external resistance. So using Ohm's law in R again, so V is equal to IR. So I'm using Ohm's law in the external circuit R, external resistance R. So I can write V is equal to IR. So I can put the value of current now. So putting the value of current from here, so V is equal to EMF by sum of resistance into resistance. So and your V will be, now I'm multiplying the things. So now using equation 1, that is E is equal to V plus V dash. So V is equal to EMF minus V dash, and V dash is IR again. So V is equal to EMF times IR. So this is the relationship. So IR is, again now I'm taking the IR this side. So I'm taking I down. So your internal resistance is E minus V by I. So again using Ohm's law, I is equal to V by R. So this R will go up. So now this is the final expression, I guess. So yeah, this is the final. So internal resistance is EMF minus V by V. So these two V's are same into R. So this is the relationship between EMF, terminal potential, external resistance, and internal resistance. So now let's prove that EMF is equal to the terminal potential. That's we are talking about is EMF is potential difference across the terminal of the cell when there is no current flowing. So let's start. So we have to prove E is equal to V when circuit is open, or I is equal to 0, current is 0. When the circuit is open, current will not flow. So EMF, for EMF we already know E is equal to IR plus IR, and these are the things what we have used. R is the external resistance, R is the internal resistance, I is the current. So using Ohm's law, V is equal to IR, so E is equal to V plus IR. So EMF is potential difference across the cell plus current into internal resistance. But it's saying open circuit, so we have to prove that when the no current is flowing. So when the current is not flowing, I will be 0. So if you put I is equal to 0, so your EMF will be equal to potential. So I can write EMF is equal to potential difference when there is no current. But when I is not 0, so that time you have to add something to this potential. That means this plus something is equal to EMF. So that means EMF is always greater than this. So now let's see the graph between EMF and external resistance. As we already know, when there is no current flowing through the circuit, that time the potential difference will be EMF. So whatever you connect after, when the cell is not circuit is not on, whatever resistance you put, it will not depend, so EMF will be constant. So as we have been telling that, so EMF is constant, it does not depend on R. So the graph will look like this, so straight line parallel to x-axis. So this is a constant EMF. So now this is V versus R graph. So we know V plus V dash is equal to EMF, and if you use Ohm's law, IR plus IR is equal to EMF. So now if I take I common, then IR plus R is equal to EMF. So if you take R plus R down this side, cross multiply, so you will get I is equal to E by R plus R. So but V is equal to IR, so I'm putting V is equal to IR out here, sorry, V is equal to IR, so I'm putting the value of current out here. From this, V is equal to I into R. So now if you take R is equal to 0, from this expression I am drawing the graph. So when is R, if you put R is equal to 0, V will be 0. So that's what I've written. When R is equal to 0, V is equal to 0. So when you put this R is equal to small r, that is external resistance and internal resistance are equal, so that time you can write this R is equal to capital R. So this, there will be 2R out here, so from here you can see R plus R is 2R, so 2R, R will get cancelled, so your potential difference will be EMF divided by 2. And when you put R is equal to infinity, so R is equal to infinity means current is not flowing. So we know that from definition also, EMF is potential difference when the circuit is open. Open circuit means infinite resistance, so that time you can write V is equal to E, or you can use the expression also. Now this same expression I am taking R common, so if you take R common, so this R and this will be wait, okay, this will be R by R. Please write this small r out here, I forgot this R. So this R by R, so this 2R will get cancelled. So next, now you put R is equal to infinity, so this will be small r by infinity, and something by infinity is 0, 1 by infinity is 0, and R is small also, so that time I can write this is E by 1 plus 0, so this will be V is equal to E. So as theoretically also we know EMF is terminal potential when R is infinite, that means open circuit. So this is the thing. So now let's draw the graph. So we'll be using when R is equal to 0, V is equal to 0. When R is equal to small r, V is equal to EMF by 2, and when R is equal to infinity, V is equal. So using this, so see, when R is equal to 0, V is equal to 0. So when R is equal to R, so this is E by 2, EMF by 2, and when R is infinity, R infinity means this side, so when you go this side, R will become infinity, so it will go to infinity, this V will become EMF. So see out here, so when it reaches infinity, it will touch this, so that means after some time, so R will become EMF when resistance become infinite. So this is the graph, three graph you have. It may come in exam, so make a note on this. Okay, the last one. So V versus I graph. So Vi versus I graph is inside the cell, not outside. Outside we already know from Ohm's law, it is a straight line passing through the origin. So let's see. So this is the equation we have been using. E is equal to V plus IR, external potential plus internal potential. So V is equal to E minus IR. So if you compare this equation, so again I am taking IR this side, and V is equal to I minus IR plus EMF. So if you compare this equation with the equation of straight line, that is y is equal to mx plus c. So c is the intercept. So if you see the diagram out here, so this is the graph for y is equal to mx plus c, and c is a point where it is touching the y-axis. So it is 2 out here, so it is touching at 2. So similarly we have our intercept as EMF. So and this m is the slope. So instead of m we have minus r, so it has negative slope. Slope means like what angle it is making with x and y axis. Okay, so next is, so that is c is constant or intercept, and this is EMF. So the graph will be the graph of a straight line with negative slope. That means out here it is going up with a positive m, but our is negative r, so it will go down. So this is the final graph. So and our intercept is EMF. So V will be, our potential will be EMF when current is 0. This is from definition also. So this is a EMF is terminal potential when current is 0. So and we have a straight line graph with negative slope, that is minus r, and that is the graph for V and I inside the cell.